So next we have Peter Denning, who was the first SIGOPS chair. He was also SOSP chair in 1977 and a founding member of SOSP and SIGOPS community in many, many aspects. He was instrumental, as I mentioned, with Jack Dennis, Butler Lamson, and others in defining a core OS curriculum in the Cosine Task Force 8, and really from the beginning saying that it was something about principles, not techniques, principles that would stand the test of time. So we are here today to pay tribute to that idea. He is going to be talking about those foundational principles that have stood the test of time. He is very well known for his fundamental work in the working set model of memory management, as well as capabilities and many other things, transition of ARPANET to NSFNet. And also he is a professor at the Naval Postgraduate School, which is right down the road from here, which is incredibly convenient also for our day today. So please welcome with me Peter Denning.
So, good morning. What I want to do today is talk a little bit about the foundations of operating system that Jack was starting to allude to. We've always been foundational in these conferences, and I want to show you what we were thinking about when we got started. The story I want to weave for you in the next 20 minutes is this story up here, that operating system principles began emerging around 1960, as you could see from Jack's talk. They grew across many generations of technologies, 50 years worth, and they left with us a rich heritage in the minds, hearts, and souls of everybody who uses computers, not just us who build these systems. In telling an overview of this story this morning, I want to start out with some timelines about how things evolved and developed. I want to include a personal example of my involvement in the, the history of one of the principles of operating systems. From this, I want to draw a few conclusions about how we do research in our community, and finally conclude that operating systems has actually been a major force in computing as a whole and not just as a specialty. In covering this, I'm going to be surfing through a lot of stuff here. I'm not trying to identify lots of personalities and systems. I'm trying to identify patterns. So you will hear more about patterns in particular systems and people who have got involved from the other speakers who go deeper into these timelines than I'm going to go. This little graph here just shows you that we're part of an ever-expanding enterprise of creating new operating systems. Wikipedia has a list of operating systems, and you can see how it grew from a small number in the 1950s. And actually, if I had Jack's slide, I would have doubled that number because he had more than was listed in Wikipedia there. But there's been a lot of operating systems registered in that time, so this continues to grow. Our history with operating systems has been going on since around 1950, but if you step back from the distance we're able to here, you can see basically 4 different styles of operating systems emerge during this time. The very first one were the batch systems, followed by the interactive systems, followed by distributed systems, followed by cloud and mobile systems. During the first period of time, operating systems were described in terms like these pictures here. So Jack mentioned one. Morris Wilks also mentioned where you had a clothesline, you hang the jobs up on the clothesline, and the operator would pull them off and put them on the machine. So that was an early system of operation. IBM automated that with the 1401 system, which it used as a front end to their 7090 series of computers. During the interactive phase, we started to see pictures like this with a big computer, lots of terminals connected to it, and the terminology of computer utility started to appear in that time. The utility idea is you could hook up these cheap terminals to wall sockets and connect in and receive computing power somehow through a network. In the distributed system era, we started to see a lot of pictures like this with lots of connections between computers. In the bar up there, the L on the left doesn't mean left, it means local. As the initial work in these systems was on local networks, but it soon expanded to include the entire internet, which is the I on the other end of it. Then in the current era, we have the cloud and mobile systems, which here I've shown also benefited from all the work done in personal computing. And now the pictures we see look like this, with portable devices somehow connected to the cloud. So if I could sum all that up, sum up a lot of work. Batch systems were focusing on one job at a time. Interactive systems were focusing on many jobs, sharing the resources of the computer on behalf of many users. Distributed systems began to get personalized and immersive, so you would have, in the Xerox days, for example, you'd have a desktop metaphor, which has actually been a very durable metaphor, that you can get immersed into that world of your desktop and your work and manage your work from your operating system. And the final current stage is that's expanded. Now you have a personalized, immersive worlds where you manage your life, you manage your social networks, you manage all sorts of things. So operating systems come a long way in 50 years. There's even a movie out now, you may have noticed, the movie Her, where the star of the movie is an operating system. These are not the same as the movies about robotics. It's another genre of movies. This is a movie where the star of the movie is an operating system. This little timeline here shows the arrival of the internet onto the scene of operating systems beginning in the late 1960s, and the pinkish color on the left side of that timeline tells us that in the beginning parts, the job of the operating system was simply to interface with the internet, and there were various programs available to do that. And as time went on, the operating system evolved and began integrating all sorts of things that were part of the network into the services of the operating system. There's a lot of, you can see a lot of these terminologies here that have come into the operating systems because of that. There's a lot of other timelines I could show here, but we don't have enough time. Fortunately, we have all of these things mentioned in the fine print there, going to be spoken about this morning and this afternoon by our other speakers, so you'll hear people digging into these things much more deeply. Not only have we been successful with operating systems as a way of principles, as a way of building and our systems, but we've also had a big influence on education. So beginning around 1970, actually, as Gina mentioned, some of us proposed a core course in operating system principles, and it was adopted as a core course. And we've always had a core course in the CS core of every computer science department since that time. So we've had a strong presence there as well. I put this arrow up here at behest of Ken Bierman. Ken and I have been working very closely on organizing this conference. But Ken thinks this is a wonderful example of how controversies rise and fall in our field. During the beginnings of when we talked about capabilities, a hot topic, there were loads of sessions and papers in the operating system conferences about this topic. In the early 80s, it sort of died out as a topic of interest. I put that to the risk revolution. Other people have other reasons for that, but our speakers today will be actually bringing this up. It's actually becoming a little hotter lately with some new ideas about open system architectures being discussed. So you'll be able to hear about this a lot today and be able to ask your own questions about it. This evening we have an open mic session with Peter Neumann, and anybody who's got capability stories or arguments they want to bring up, welcome there to try it out on the group, see where we are. Now let me turn now to digging in a little closer, development of principles, which is what we've been all about. So the first question is always, what is a computing principle anyway? We talk about this. Well, one big category of computing principles is a law. A law is a statement that has to do with how we do computation or some part of computation that's always true. For those who don't know what I'm talking about, here's 4 examples. There's many more. The first example is a semaphore invariant that was proposed by Nico Haberman a long time ago, which tells us how many semaphore completions can be completed up through a certain time. He introduced this as a way of making proofs about critical sections and other uses of semaphores. The second line there says that the amount of memory used by a multiprogramming set of computations is equal to the space-time per computation multiplied by the throughput of the system. This is a fundamental law that the memory management people are aware of this. A lot of other people aren't. But those who, the original intuition about minimizing space-time was because of this law here. We used to have a lot of coverage in operating system conferences on performance issues. Some of the people that did that created a big algorithm for evaluating queuing networks called mean value analysis. And especially in the early days of this conference, there was a lot of papers on memory management and locality. So these are examples of 4 things that fall in the category of laws. In addition to laws, principles also include what I call statements of design wisdom. These are not necessarily laws, they're accumulated things that we've gathered in our community to help everybody do things better. So there's many of these, but here's a couple of them. Information hiding is like this. It's a guideline for how we organize programs. Levels of abstraction, which we use a lot in organizing complex systems, is another one we've done a lot of work with. So there's a lot of these things that fall in the category of advice on how to do design well. A third thing here, this is not so much a principle or a law. This is a guideline about, well, how do you decide if somebody walks up to you and says, here's a statement which I propose to be a principle. How do you decide whether you should actually include it? Jim Gray said, well, it should be cosmic. You know how Jim talked. It should be cosmic. And he meant timeless and spaceless. So it's always going to be true in all parts of time, for all time, and it's going to be spaceless, meaning that no matter where in the universe you are, not that we can actually perform the experiment, but it will also be true. So that was how he was going to sort things out. In the area of operating systems, he said to me one day that locality is a cosmic principle. Virtual memory is a brilliant idea, but it's not a principle. So that sort of made me feel good and bad at the same time. By the time the middle 60s, all the experimental systems that Jack Dennis was referring to had all developed some ideas about principles of how you build operating systems, and they all kind of came together in what was then called the 3rd generation of systems. So you see things like hierarchical file system, fault tolerance, interrupt systems, virtual memory, multiprogramming, modular programming, interactive programming, and controlled information sharing, all kind of coming together, and the job was to try and integrate them into a single operating system, such as Multics or OS 360. At around the same time, the people who are building systems said, we've got to use high-level languages to build our systems. They're just getting too complicated. We can't do it in assembly language anymore. The process that was initiated and has been carried out through all of our work and the operating system conferences gave a number of important fundamental OS principles that we said are important to OS. They became general principles that people mention all throughout computer science. So interactivity is a principle that we were always working with, and in recent years, the theoreticians have figured out that interactive computing, which combines humans and machines working together, can actually compute functions that Turing-complete computation can't. We were the ones who perfected the concept of a process and concurrent processes and how you synchronize them. We developed and verified the principle of locality. We worked out all sorts of ways of naming things and mapping names to the objects. We developed methods of protection and sharing. We spent a lot of time on virtualization. And finally, we spent a huge amount of time on system languages so we could describe what we wanted our systems to do better and have them actually work. In about 1964, I did a survey of the great principles of computing. There's a website if you're interested in looking at it, but in that survey, 13 of the 41 cosmic Jim Gray principles that we had listed at that time were from our field, operating systems. So that's about a third of all the CS principles that people work with come from the work this community has done over the years. Gina mentioned this thing here is a group of us here, some of us, most of us are in the meeting here, was asked by NSF to put together a proposal for a core course in operating system principles in 1970. A report came out in 71. To do this, we had to expand the definition of core to include systems. At that time, core was math. It was switching theory, algorithms, parsing, compiling theory, numerical analysis, and a couple of other kind of math-like courses. So this was kind of a radical idea that systems deserved to be part of the core. We obviously succeeded in our argument. It struck a resonant chord with many people, and operating systems has been a core course, unchallenged in all the ACM, IEEE computer science curriculum reviews for 44 years. Now, I want to talk a little bit about one of the things I'm most familiar with, which is the line of work I was involved in, just to give you some examples of what's going on here. This is the emergence of the locality principle. For me, this was a big adventure begun when I was a graduate student at MIT in Project Mac. I became involved with this in 1965. My advisor was Jack Dennis, and he started saying, you've got to help us understand this problem. Over the years, there's many people been involved with this. There's been memory management sessions throughout operating system conferences for almost 50 years. So by my count, there's been thousands of people involved in looking at these issues. The first motivations which were presented to me around 1965 were these three here. Performance of virtual memory is a whole assortment of proposals for paging algorithms, and people were getting mixed results. And the Multics people wanted to know, can we successfully do a virtual memory? And so they thought maybe a graduate student could solve this problem in a few weeks or something. Also, multiprogramming was a new issue. How do you deal with memory management in a multiprogramming environment? Do we have fixed partitioning, variable partitioning, et cetera, et cetera? And finally, a big issue was thrashing, which was the performance collapse observed in the early virtual memory multiprogramming systems. This is a curve that we often use to describe thrashing. The horizontal axis here is the amount of programs, the degree of multiprogramming that are loaded into the main memory. The black line is the actual throughput of the system as a function of the number of jobs. The little dotted line in the upper right is the expected performance of the system by the designers at that time. They thought if you keep adding jobs to multiprogramming memory, things would gradually, the throughput would gradually increase and then saturate at the system limit. Well, it actually reached some optimum point and then collapsed. And nobody knew how to predict where the optimum was. This whole thing was a big surprise. It was also a big liability. So here's all these operating system builders putting together major systems, and they're going to put them out there, and their customer is going to say, you expect me to pay $1 million for a system that's going to crash? Or thrash, not crash. Well, being aware of this, Jerry Salzer gave me a challenge. He said, this is something for you to think about. He said, the blue box represents our computer. There's some kind of performance meter on it, giving a measure of performance, which might as well be thought of as throughput, and some tuning buttons. And what we want to do is have one parameter which can be set once through the tuning buttons to maximize the performance of the system, and then leave it there. And the system would continue to run at that level. And so that was, I call that Salzer's challenge. using the thrashing picture I just showed you, he's saying, can we find that optimum point on that thrashing curve and have the system lock in on that point? Well, this picture here summarizes a lot of what we have learned. This is a memory map, a reference map of a computation. It was actually a Firefox browser operating in about 2005. A student in England named Adrian McMenamin collected this data and collected a lot of other data. But these are pictures of how a program uses its virtual memory. The pixels in the picture, the colored pixels, mean that during a certain small time slice on the horizontal axis, that page of virtual memory was being used. So you can see some very distinctive features of this picture, like there's a lot of white space. So there's a lot of, and during long intervals of time, there's a lot of virtual memory that's not used. There's a lot of stability. You'll see long periods of time when the set of pages that are being used in the virtual memory is fixed. And then there can be some sharp transitions to other locality sets. By the way, the time slices on this thing are 375,000 instructions. So these are pretty fat windows here, but you can see a definite pattern. Now, we had people doing reference maps like this way back in the 1960s, looking at performance of virtual memory systems, and the same kind of thing always showed up. And these were the first glimmers of locality. There's something going on in the program that localizes the way the reference happens. And the question was, is this a universal phenomenon, or just a few programs have this? And if it is a universal phenomenon, how do we harness it to do good? The idea that I participated in to help work with this called the working set, and basically the set of pages using a virtual time window of size some amount t, trailing behind the current moment. You can think of it as a vertical slice in the reference map. Over the years, all of us who looked into these things learned a lot. So by 1980, this is what we knew. First of all, the working set equals a locality set most of the time, like 97, 98% of the time. Second, working set policy, which means load only the pages of the working set and make sure you never throw them out. You protect them. That policy is very close to the theoretical min policy if the program has locality. Theoretical min means you can't have fewer page faults than that. There's been some very economical implementations of this idea built up. The mathematical model of it leads to ideas that are very inefficient, but there's been very efficient things. For example, in one of our conferences, there's the working set clock algorithm. The working set policy prevents thrashing, and we also demonstrated that it answers Salter's challenge, that the working set will lock in on the one value of the working set parameter that will keep the system from thrashing and operating at its peak throughput. So the locality principle, by 1980, all those initial intuitions were confirmed by many experiments on many systems. The conclusion was all computations display locality. This is an empirical conclusion. And then recently, the algorithms theorists got into this and concluded that you can't even have an algorithm if the instructions of the algorithm aren't restricted to a local area of your data space. So this is a theoretical requirement for computation to exist. And all of our experience says that harnessing locality always pays off. So caching, parallelizing, performance, and no thrashing are all benefits that we got from harnessing locality. Now, in the process of doing this, I learned some things about how we in this community do research, and I've also talked to many of the people who've done the research, and these kind of conclusions show up in everybody's story. First of all, there's never certainty. So we often say, we really don't know what we're doing, which is the way we feel. So we're always taking stabs at things, trying to find things out, but we really don't know what we're doing. We learn. Occasionally we come across an insight that sets a new direction, and we follow the new direction, maybe get a little further. Occasionally, we come across a technology inflection point, which some of our speakers today will talk about some of these things, and they trigger avalanches, where avalanches are big changes of practice in the community that sweep away a lot of old stuff. We're always searching for what works and what doesn't work. So we're building, we're experimenting, we're tinkering, and that's how we learn. All of our research is always done in a social network, meaning that there's always users out there, there's always ourselves, there's always other people using our systems, and we have to take that into account. And finally, in our area, we have theory, but it always follows the practice. Very, very little in operating systems was somebody proposing a theory and then a lot of people running out to test it. It was more the other way around. People were observing things and asking, can we achieve a deeper understanding of what we've been observing through theory? So this is a kind of a signature of what we do in our research. So with that, I'm going to finish my surfing here and just summarize the things I'm trying to point out here. First of all, as you will see as we go on through the day and also from all these timelines, is we have a rich heritage that we've inherited from thousands of researchers who've come before us. And a lot of the things that we are concerned about today are concerns that have existed in our field for many years. In the process of doing this, we've evolved through the batch, the interactive, and now the immersive styles of operating system. A number of fundamental CS principles emerged from our research and were accepted by the entire computing community as part of what we consider computer science to be all about and what should be in our curriculum. And the operating system principles drove major changes to the computing curriculum and initiated a process where systems courses got accepted into the core of computer science. Operating system research, as I just said, is a unique blend of engineering, experimenting, and modeling, which I'm very proud to be part of, and it's what we do. We don't always know what we're doing, but we always seem to get somewhere and produce good results. And I can't end without saying something about the future that we face. So here's a few challenges that we as operating system researchers need to deal with. One of them is the automation of knowledge work. So our operating systems are being used to help automate a lot of tasks that we formerly thought were cognitive tasks that only people could do and not machines. Well, that old belief is being upended in the last 10 years. And our operating systems are part of it, and we're involved in the designs of trying to figure out how we don't make a disaster out of this. Second thing is that the network has now changed from being a connection of routers and links into a social space where people have power, identities, concerns, and everything else, and we have to take that into account when we design. Security and privacy, which has always been an issue in operating systems, has now become a really big issue, and the internet is being exacerbated with the Internet of Things. Tonight, at the end of today, we have a big session on the future of computer security, and you'll be hearing more and more about this, and you'll have a chance to ask your own questions. The systems that we are trying to deal with continue to grow in size, complexity, and scale, and we have, as designers, to deal with that. And finally, there's other technology areas, notably the biotech and the nanotech, which are starting to appear and be integrated with the work we do. So I don't have any answers to any of these things. To me, they just look like challenges that lay ahead that we're going to have to be dealing with as we continue. So that is the end of my story for today, and I thank you all for listening.
We are somewhat miraculously kind of on schedule, so I think we could take a question, if anyone would like to try that. I think maybe if you had a question, you would just ask it, and I would repeat it into the mic for the record. Anyone want to brave a question? All right, well, think about it. Oh, okay, here we go.
Nobody else wants to have a go. So, this whole story about principles is sort of led us to a point where we have some fairly well two ideas are still being tied down, because it's much harder right now, if you're an undergraduate student nowadays, if you're a graduate student nowadays, to really challenge things. Obviously we're probably not going to challenge locality, but other things is the way how the world works. They are, as you said, sometimes coincidence of history, sometimes good ideas, sometimes ideas that change over time. But we have to give people reason to challenge these things, right?
So I'll quickly summarize this. How do we think out of the box? How do we...
Well, when you put it that way, there's something to be said for boxes. If we didn't have boxes, we wouldn't know how to think outside of them. But I'm not worried about our field becoming mathematized, if I could put it that way. The traditions of mathematics they do flavor what we do, obviously, because we do have formalisms. But in our field, our formalisms have always been following behind our engineering. So in our case, our science is inspired by the engineering, the advancement of the technology, the new designs that we have to come up with to deal with all these challenges that keep coming at us. So we're always going to be in that kind of